Good morning. Today we are going to discuss two topics, that is properties of nuclear force and stable nuclei. So moving on to our first topic, nuclear force. We know that these nuclear forces are responsible for keeping the nucleons together. Since nucleus is stable, there must be a force which keeps the nucleons together. And this force is called nuclear force. Let's have a look on the different properties of nuclear force. First one, the nuclear force is a short range force. That means this nuclear force is appreciable only when the interacting particles are very close. That means at a separation of order of 10 raised to minus 15 meter or less. That means you can see this nuclear force inside a nucleus. You know that the radius of the nucleus is of the order of 10 raised to minus 14 or 10 raised to minus 15 meter. So this nuclear force is appreciable only inside this nucleus. And at greater distances, that is greater than 10 raised to minus 4 meter, this nuclear interaction will become electromagnetic interaction. Now the next point is, this nuclear force is independent of electric charge. We know this nuclear force exists between neutrons and protons inside a nucleus. Proton is positively charged and neutrons are neutral. So even though there is a difference in charge, the nuclear force that exists between two protons or two neutrons or between a proton and a neutron will be the same. That means nuclear force is independent of electric charge. Next property, it depends on the relative orientation of the spins of the interacting nucleons. See, if there exists a nuclear force between a proton and a neutron, that force depends on the spin of this proton and neutron. So it depends on the orientation of spins of interacting nucleons, and this concept was confirmed from nuclear energy levels. We had seen that since electron is having energy levels, similar to that, nucleons can also have separate energy levels. That is, there will be energy levels for protons and energy levels for neutrons also. So confirming from nuclear energy levels, we can say that nuclear force depends on the spin of the interacting nucleons. We can say that when the two nucleons having their spin parallel will have an energy different from the energy of a system having one nucleon with spin up and other with spin down. Now the next property, this nuclear force is not completely a central force. We know that it depends on the distance, isn't it? We had said that it's a short range force that exists only if the distance is 10 raised to minus 15 meter, isn't it? So we can think it of a central force, but it's not completely a central force, because for central forces angular momentum is always conserved. But in the case of deuteron, for example, the orbital angular momentum is not conserved. So we can say that nuclear force is not completely central. Next point, we know that nuclear force is a force holding the nucleons together. So it's an attractive force, isn't it? But at very short distances, that is much smaller than its range, that is 10 raised to minus 15 meter, this nuclear force will become repulsive force. So these are the different properties of nuclear force. Now we can move on to the meson theory of nuclear forces. That is how a nuclear force exists between these nucleons is explained by Japanese scientist Yukawa. According to him, all nucleons consist of identical cores surrounded by a cloud of one or more mesons. That means you can think neutron and proton surrounded by a cloud having a particle called meson. And these mesons may be charged or neutral particle. Here we can say that the mesons, we had already studied in the classification of elementary particles that mesons consist of pions, kaons and eta meson, isn't it? Here mesons means pion family. That means mesons may be charged, that can be pi plus or pi minus, or neutral mesons like that of pi 0. So Yukawa proposed that each nucleon, either proton or neutron, is surrounded by a cloud of pions, and the difference between a proton and a neutron is due to the difference in the composition of their corresponding meson clouds, or we can say pion clouds. So which type of pions are surrounded over a nucleon makes it either a proton or a neutron. Once again, all nucleons consist of identical cores surrounded by a cloud of one or more mesons, and they can be charged like pi plus or pi minus, or can be neutral. And this difference in the composition of the meson clouds makes a nucleon either a proton or a neutron. Now, what will these nucleons do? Since all nucleons are surrounded by pions or mesons, so every nucleon continuously emits and reabsorbs pions. So what happens when this pion is exchanged between nucleons? See, this proton, you can imagine thinking of a proton and a neutron interacting with each other by exchanging pions between them. So what will happen? Think this like a ball passing between two persons. So a person who is catching the ball will move backward, and the person who throws the ball will move forward. So there is a transfer of momentum, isn't it? Or change in momentum takes place in the case of a person. So that change in momentum, according to Newton's law, you know that the change in momentum corresponds to a force, isn't it? Similar to that situation, we have protons and neutrons inside a nucleus, and these protons and neutrons are continuously emitting as well as absorbing the pions, so that there is a transfer of momentum associated with them. This change in momentum will cause a force, and that force is called nuclear force. So the transfer of momentum associated with the shift of pion or exchange of pion is equivalent to the action of the force, and that force is called nuclear force. So nuclear force is the result of exchange of pions between the nucleons. For example, you can see a neutron is emitting a pion, negatively charged pion, and it becomes a proton. So that neutron giving proton plus pi minus. So there a neutron is emitting a pion. Now what happens to a proton on the other side? The proton on absorbing a pion, nearby pion pi minus, will become a neutron. So continuous emission as well as absorption of pions takes place in between the nucleons, so that this transfer of momentum or change in momentum will correspond to a force which is known as the nuclear force. Now you can see that a proton converting into a neutron by emitting a positively charged pion pi plus. So proton becomes neutron plus pi plus. On the other side, the neutron can absorb a pion pi plus and it will become a proton. You can check for charge conservation in this equation, and you can see that the law of conservation of charge is satisfied here. So that's about the meson theory of nuclear forces put forward by Japanese scientist Yukawa. Now we are moving to our next topic, that is the stability of nucleus. How can we say that a nucleus is stable? We can say it depending on the number of neutrons and protons it has. So here you can see a graph having proton number along x-axis and neutron number along y-axis. So it's an NZN graph, and this curve is known as stability curve. And you can think that if what happens if n is equal to z or if z equal to n, we will get a straight line, isn't it? So that straight line is plotted there. But our actual line of stability, you can see it above that of the straight line, isn't it? That means the line of stability get departed from n is equal to z line. So this curve is known as stability curve, that explains the stability of nucleus depending on the number of neutrons and protons it have. The first point, see, you can see for lower proton number, you can see that both the line of stability as well as the straight line n equal to z is approximately equal for lower proton number z, isn't it? That means n is equal to z, number of protons is equal to number of neutrons. So that is a case of nuclei having A less than or equal to 40. That means for mass number A less than or equal to 40, the nucleus will have same number of neutrons and protons. But as proton number increases, you can say that the line of stability get departed from n is equal to z line. That means the number of neutrons get increased. So as A greater than or equal to 40, number of neutrons is greater than number of protons, that is n greater than z. As the number of protons increases, what happens? Just think, inside a nucleus, as the number of protons increases, what happens? Protons are positively charged, isn't it? So what happens? There is Coulombic repulsion between these protons. So it will be difficult for the nucleons to be holded together when the number of protons increases, because the Coulombic repulsive force will tear the nucleus apart as the number of protons increases. So in order to balance that, more number of neutrons are required, so that the nuclear force between the neutrons and protons balances the Coulombic repulsive force between the protons. So as the number of protons increases, the Coulomb force between the protons increases and it affects the binding of nucleons. Now, as we said earlier, nuclear energy levels also exist, since nucleons are fermions with a spin half cut, which obeys Pauli's exclusion principle. So each nuclear energy level can contain 2 neutrons of opposite spin and 2 protons of opposite spin. You know how to fill the electrons in particular states, isn't it? We had studied the electronic configuration for filling the electrons in energy levels, isn't it? Similar to that, both neutrons and protons can have energy levels, with each energy level contains 2 protons of opposite spin and 2 neutrons of opposite spin. And these energy levels in nuclei are filled in sequence in order to achieve configuration of minimum energy and maximum stability. You can just think of how you have filled the electrons in several energy levels. We will draw the spin up and spin down from the lower energy levels, isn't it? So that lower energy levels are filled first in order to attain maximum stability. Similar to that, on getting a nuclei, we can check for the neutron number and proton number, and we can draw that several energy levels, both proton and for neutron, and can fill the protons and neutrons in each energy level, so that each energy level will contain, each nuclear energy level will contain 2 protons and 2 neutrons of opposite spin, so that it will attain maximum stability with minimum energy. So as the number of protons increases, the Coulombic repulsive force increases, so that it will try to tear the nucleus apart. So in order to balance that, more number of neutrons are required, so that between these neutrons and protons, nuclear force, which is charge independent, will produce an attractive force, and that force is required for stability. So as the number of protons increases, the Coulombic repulsive force increases, so that an excess neutron, which produces attractive nuclear force, is required for stability, so that N versus Z curve departs from N is equal to Z line. Now 60% of stable nucleides have both even Z and even N. If N and Z are even, that nucleus are known as even nucleus. And mostly 60% of these stable nucleides are of even nuclei. Then nucleides with even Z and odd N, that means even odd nucleus. Also nucleides with odd Z and even N will be odd even nucleides. And we are having only 5 stable odd nucleides. Odd nucleides means Z is odd and also N is odd. And there are only 5 stable odd nucleides, that are H12, Li36, Be510, N714, tantalum Ta73 180. So these are the only 5 stable odd nucleides. Now we had already said that as the proton number increases, more number of neutrons are required so that the attractive nuclear force, which is independent of electric charge, will balance the repulsive Coulombic force so that the nucleus will be stable. But there is a limit for the number of neutrons to get increased, and the ability of neutrons to prevent the break of a large nucleus is limited. We cannot provide more number of neutrons so that the nucleus must be stable. But it's not like that. There is a particular limit up to which a number of neutrons can be account for the stability of the nucleus. But after that limit, the nucleus cannot be stable. And the heaviest stable isotope is bismuth 83209. So the ability of neutrons to prevent the disruption of large nucleus is limited. And this limit is represented by bismuth, which is the heaviest stable isotope. So what happens to all the nuclei with Z greater than 83 and A greater than 209? That means after bismuth, what will happen to all that nucleus? That nucleides are unstable. So what will they undergo? Radioactivity, the process of radioactivity. That means they are unstable. So either they will transform into lighter nuclei by the emission of one or more alpha particles, or by the emission of beta particles. So all the nuclei with a Z greater than 83 and A greater than 209 spontaneously transform into lighter ones by the process of radioactivity, which you know that by alpha emission, that means by the emission of a helium nuclei, or by beta decay, that means by the emission of electrons from the nucleus. So the maximum limit of a stable nuclide is bismuth, and after that the nucleus will attain stability by undergoing several decay processes like radioactivity. Thank you.